All right, good morning, everyone. So, first of all, let me bring your attention to here. Midterm 3 is next week. So, let me tell you what it will cover first. So, it will be weeks actually 9, 10, and 11. Okay, so you don't have to worry about week 8. The other thing is, with respect to the homework, so we will, so obviously there won't be a homework writing session next week, but we will post the homework maybe like tomorrow or Saturday, and it will be due basically not this Wednesday, but the Wednesday after. Okay, so you will have about 2 weeks to work on that. And when there's the carnival, so there won't be any class on Thursday, next Thursday, and no office hours, nothing. So the course will, class will shut down for that event. Okay, so that's that. So let's get started with today's lecture. All right, so today's topic is Markov chains, which is a very nice topic. It has lots of applications, not just in theoretical computer science, not just in practical computer science, but also in other areas like physics, chemistry, math, and other engineering areas as well. But before actually I tell you what a Markov chain is, let me tell you a bit about myself. Okay, so in case you were wondering what I do all day. So I come to work at 9 a.m. That's a lie, but let's suppose that I come to work at 9 a.m. Start working, okay, at 9 a.m. Maybe do some math. Well, these days it's more like preparing slides, I guess. Then at 9:01, there will be a 60% chance that I will start surfing the web. I'll probably go to mba.com and check out the results there. I probably spent too much time there. But there will be 40% chance that I will keep working. Now, if I am surfing the web at 9:01 a.m., there will be a 30% chance that I will move to checking my email, 60% chance that I will keep surfing, and 10% chance, a small chance, that I will go back to work. Now, if 9:02 a.m. I am emailing, I'm checking my email, then at 9:03 a.m. there will be 50% chance that I will keep checking my email, and 50% chance I will get back to work. Okay, so these are sort of the 3 different states that I can be in the morning: work, surf, email states. And you can imagine me, so I start going back to 9 a.m. now. So I start at this work state, and then I basically follow these arrows probabilistically. So maybe at 9:01, I will be at surf because 60% chance I was going to go to surf. At 9:02, maybe I stay in surf because I have 60% chance staying in surf. Maybe at 9:03, I go to email. Maybe 9:04, I stay in email. And then maybe 9:05, I come back to work. Okay, so that's my typical morning. But enough about me. So let's talk about Markov models. So 2 things. So there's the Markov and the model. So here's Markov, Andrei Markov, 1856 to 1922. He's a Russian mathematician. He worked on random processes. So maybe you've heard about Markov's inequality from probability theory. It's a very fundamental inequality. It's the same Markov. Same guy. So he spent a lot of time on random processes. And I guess he spent a lot of time on his beard and tried to make it pointy. And he was successful in both areas. So the model that we are going to discuss today is a model for the evolution of a random system. It's going to be a very general model. The only requirement that we have is the following. The future is independent of the past given the present. Okay? So that's the random model that we're after. So we're after these random processes that satisfy this requirement. And if you think about it, a lot of the random processes do satisfy this requirement. And I will actually show you lots of examples and convince you that this is the case. Okay, so what are the cool things about the Markov model? As I said, it's super general. And therefore, it has like an enormous number of applications in many different disciplines. So not just in computer science, as I said, math, biology, physics, chemistry, economics, psychology, music, baseball. Okay, so whatever you can think of, there's an application of Markov model there. It's as I'll show you, it's a very simple model. It's a neat model, nothing too complex. And there's a beautiful mathematical theory behind it. It starts simple, some simple probability theory, some simple linear algebra. But it goes deep. As you go into more sophisticated areas, there's some nice mathematical theory there. So what I'm going to do in this lecture is I'm going to start with some motivating examples and applications of Markov chains. After we, at a high level discuss these applications and examples, I will go into the basic mathematical representation and the properties of Markov models. And then I will discuss in a bit more detail a few of these applications. Okay, so let's start with some basic examples. And again, just keep in mind that we are in the setting where the future is independent of the past given the present. Okay, so some examples of Markov models. So here's the first example. Okay, so a drunkard walk. So this is me on a Saturday night. Okay, so think of this as a map. Okay, this grid as a map. The blue lines are roads. The red dots are intersections. Okay, so I come out of the bar. The bar is in that intersection. I want to go home, which is here. Okay, the thing is, I'm like super drunk. So at every intersection, I completely choose a random direction to go. Okay, so there's going to be like 1/4 chance I go north, 1/4 chance I go east, 1/4 chance I go west, and 1/4 chance I go south. And each intersection is the same deal. There's like completely random, I pick a completely random direction. And then you can ask, okay, what is the probability that I will eventually end up home? And you can also ask, like, what is the expected time if I end up at home? What's the expected time for me to go to home, and so on. Okay. So that's one example. And if you see, like, once I am in some intersection, which direction I will go doesn't matter. It's not dependent on how I got to that intersection. All that matters is that I'm at that intersection, and the next place that I'm going to be at will be based on where I am currently at, and not based on how I got to that current position. Okay. Diffusion processes. So if you look at, for example, so these lines here represent the movement of, let's say, 3 different particles in space, the way they diffuse in space. And you can, I'm not a physicist, but you can sort of convince yourself that where the particle will end up in at the next time unit depends on where it is right now. And it does not depend on how it got to that location. But once it's in that certain location, where it will go next Just depends on where it is currently at. So that's a Markov process right there. Let me give you a very extremely simplified model for the weather. Okay, so let's say that I observe these following probabilities. So I see that if it's currently sunny, the next day it's going to be rainy with probability 10%. If it's currently sunny, it's going to stay sunny with probability 90%. If it's rainy, it's going to stay rainy 50%. And if it's rainy, it's going to become sunny 50% of the time. So I might have some model like this. I can actually equivalently describe this model as a directed graph, where I have two states, sunny and rainy, and I have these transition probabilities. So if it's sunny, it will stay sunny with 90%. If it's sunny, it will become rainy with 10%, and so on. So these are equivalent representations of the same system. Here's a third equivalent way of describing it, and this is the in matrix notation. Okay, so you can label each row and each column by the states, sunny and rainy, S and R, and you say, okay, if it's sunny, the probability that it will stay sunny is 0.9. So the SS entry in the matrix is 0.9. And of course, yeah, this is super simplistic model, but you can actually encode more information about the current state. Maybe you want to encode the pressure and the humidity and so on. You can build a more complex system which is more accurate. Okay, here's another example, life insurance companies. So life insurance companies, they want to figure out what amount to charge you, okay? And to do that, they have to know, they have to have some kind of a model about how long you're going to live, okay, so that they can decide how much to charge you. So this can be actually perhaps modeled with a Markov chain. So you can have some certain probabilities, like if you're healthy this year, you're going to become sick next year, maybe with 30% probability. If you're sick this year, you're going to be healthy next year with 80% chance, and so on and so forth. Again, you can build an equivalent directed graph. If you're healthy, you stay healthy next year with 69%. You die with 1% chance. If you're dead, hopefully you stay dead. Right? And you can have an equivalent, as I said, matrix representation as well. All the information that's encoded in here is also there, and vice versa. Okay, so here are some applications of Markov models. I don't know if you're going to be able to hear this. So this is algorithmic music composition. So a computer basically is automatically generating music. And okay, so you won't be able to hear it, but anyway, it's not bad. It does generate some nice sounding music, totally automatically generated, and this can be done using Markov chains. Image segmentation is another like computer science area where you have some image and you want to determine, let's say, which part of the image is, let's say, the background, which part is like the face of a human being, which part is an animal, and so on and so forth. So that's like image segmentation. And you can use Markov models for this. So the user first labels some parts of the image with some colors, and then you run the Markov model, and it fills out the rest for you automatically. And then you can make some corrections and so on. Automatic text generation, again, this is kind of a funny application. So you can actually generate random text. A computer can generate random text like putting random words together using a Markov chain. And you can get sentences like this. While at a conference a few weeks back, I spent an interesting evening with a grain of salt. So you can Google Mark V. Cheney to learn more about that. Speech recognition. Actually now, like most of your phones have this property that it can recognize and understand what you're saying. And this kind of thing also use Markov models. Google PageRank. This is probably one of the more famous applications of Markov chains. So you probably don't know this, but in the late 1990s, web search was pretty bad. So I guess I'm assuming this was the time, around the time you were born. So while you were being born, we were like really suffering with the internet. So the most famous search engine at the time was like Alta Vista. And the way it did things, the way it ranked web pages when you search for something was very extremely simple. It just sorted by the number of occurrences of the keyword. Like really, like very simple idea. So it didn't work well, obviously. And then there were two guys at Stanford University, graduate students at the time. They had an idea of like using Markov chains to rank web pages. And you know the story, then they became 20 billionaires. And actually, this guy, John Kleinberg, who probably you don't know, had the same idea. The thing is, he didn't like form a company with that idea. So he's not a 20 billionaire. But he did win like the Nevenlina Prize, which is like the, in some sense, the Fields Medal for theoretical computer science. Okay, or like Nobel Prize for theoretical computer science. So he did well as well, I guess. Now, how does Google rank the web pages that you see? So the way it does it, there are two important factors, of course. One is the relevance, right? The web page should be somehow relevant. But the other thing is how important that web page is, how its reputation, right? So a web page like CNN.com is going to have more reputation, more importance than my personal web page, for example. Now, I'm not going to talk about the relevance of the web page, but let's now look at the reputation of the page. How would you measure the reputation of a web page? So the way they did it is basically they defined it as the reputation of a web page as the number and reputation of links pointing to you. So for example, if CNN.com has a link that points to my personal web page, then that makes my web page important. It makes it have high reputation. Can someone tell me what's interesting about this definition?
It has nothing to do with your page?
No.
Kind of cursive?
Yeah, it is circular. I'm defining the reputation by the number and reputation of links pointing to you. What's remarkable is that this is not a problem. Okay, so you would think that that would be a problem, that if you define it in the circular way, you know, that's not a good definition, that's not a well-defined concept. But it turns out that this is okay. With Markov chains, we will see that this kind of definition actually works. So the reputation measure used by Google is called PageRank. Okay, and this PageRank is calculated using a Markov chain. Okay, and I hope at the end of the lecture I will have a bit more time to say a few more things about this. Okay, and now of course, you know, web search is much more complicated than this. If you ask like Google, what is the answer to life, the universe, and everything, you get the answer 42. Right? So Google, of course, now does much more complicated things behind the back, but at the heart of everything, there's still PageRank there in the software. At least that's what they tell people. Okay, so that's the first part of the lecture. Now let's move on to the basic mathematical representation and properties of Markov chains. Okay, so in general, this is going to be our setting. We're going to have n possible states or values, and at each step, at each time unit, the state is going to change with some probability. Okay, as we saw, you can represent a Markov chain basically with a directed graph where the nodes correspond to the different states. And for each node, there are a number of edges going out of that node. And notice that if you sum the probabilities for each of those edges that are going out of a certain node, that's going to sum up to 1 probability. So this is, let's say, one Markov chain. Here is another one that we saw, sunny and rainy Markov chain. Note that it has the memoryless property that we discussed. So the next state only depends on the current state and does not depend on how you got to that current state. And the evolution of the system, you can start at some certain state and ask, how does the system evolve? It's basically a random walk on this directed graph. Okay, so you can imagine, so let's say I tell you, okay, we're going to start at state 1. Then you can imagine, the drunk guy, okay, being at state 1, and he does this, his drunk walk, his drunk random walk, according to these probabilities on the edges that go out of that state, right? So starts at state 1 with probability half, he's going to go to state 2, and probability half is going to go to state n. So maybe he goes to state 2. Then when he's in state 2, well, he actually has no choice. With probability 1, he's going to go to state 3. In state 3, he has no choice. With probability 1, he's going to go to state n. When he's in state n now, he has 1/4 probability of going to state 2 and 3/4 probability of going to state 3. Maybe he goes to state 3. Then he has to come back to state n. And then maybe he goes to state 2. And then he goes to state 3, and so on. So you can see this guy just randomly walking on this directed graph. Okay, so here's another example. This is the Markov model for a lecture. Okay, so you come into the lecture, that's the first state. You arrive, you have half probability. You're going to start playing with your phone. I know it. Now, if you're playing with your phone, you're going to have half probability that you're going to keep playing with your phone. But with 1/4 probability, I will notice it, and I will kick you out. And once you're kicked out, you stay kicked out. So anyone using their phone? Okay, so let me introduce a bit more notation about the setting. So as we said, we have n states. The system evolves probabilistically. We're going to let x sub t be a random variable. And it's going to be the value of the state at time t. Okay, and obviously it's a random variable. It's not determined. So when you look at the evolution of the system, it starts with x0, then it's x1, then it's x2, x3, and so on. It goes on like that. And x0 is some initial state. It can be a deterministic state. You can say the initial state is always 1, let's say. It can also be a probabilistic state. It can be a probability distribution over the states. But once you're given x0, so this would be explicitly given to you, then you can try to determine, okay, what's going to be x1, what's going to be x2, what's going to be x3, according to the directed graph and the edge probabilities you have. So the memoryless property, how can we express it in terms of these random variables? Well, you can say the probability that x sub t is in a certain state is determined by x sub t minus 1. Okay, and if you want to be like very precise about what that means, here's what it means. It means that the probability that the xt random variable is equal to some state x, given that x0 is like this state x, small x0, x1 is small x1, and so on and so forth. That's going to be equal, exactly equal to the probability that xt is equal to x, given just the last step, xt minus 1, given small xt minus 1. Now, if this is like makes you a bit uncomfortable, it's okay. Like you don't have to think about the Markov chain in this way. You can just think about the directed graph and the probabilities, and it's like a random walk on this graph, and that's totally fine. Okay, so let's say we start at state 1. When I tell you that the initial state is state 1, what that means is that this random variable, it's not really random, but this random variable x0 has the probability distribution 1, 0, 0, 0. This distribution I'm going to denote by pi sub 0. So what's the interpretation of this? If you look at this vector, what it's saying is, with probability 1, I'm in state 1. Probability 0, I'm in state 2. With probability 0, I'm in state 3, and with probability 0, I'm in state 4. Okay, so that's the way you interpret that. Now, if I ask you what is the probability that x1 is equal to 2, given x0 is equal to 1, 1/2. What is the probability that x1 is equal to 3, given x0 is equal to 1? That's 0. What's the probability that x1 is equal to n, or 4, given x0 is equal to 1? 1/2. And what's the probability x1 equals 1, given x0 is equal to 1? 0. And let's say t is any number bigger than 1. What is the probability that xt equals 2, given xt minus 1 equals n? Anyone? 1/4. What is the probability that xt equals 3, given xt minus 1 equals 2? 1. Good. Okay, so that's the interpretation of this, another interpretation of this graph. As we said, there are two different but equivalent representations of a Markov chain. You can draw the graph, directed graph. You can write the matrix. The matrix is called the transition matrix. Okay, and for 251 purposes, we're going to make some assumptions. First, the assumption we're going to make is that the number of states is finite. And the second assumption we're going to make is that the underlying graph is strongly connected. So what does that mean? It means that if you take any two nodes in the graph, S and T, let's say, there has to be a path from S to T and also a path from T to S. Okay, so between any two pairs of vertices, you have to have this connectedness property. That's why it's called strongly connected. Okay, so it's possible to reach any state from a given state. So you can ask now some very interesting fundamental questions about a given Markov chain. Question?
Wait, so in the example you gave earlier where once we were in the death state, we stayed in the death state, that wouldn't be allowed?
That would not be allowed. Yeah. Correct. So what is the probability, for example, we can ask that we'll end up in state I after t steps? So I can ask you, I give you a Markov chain and I say, okay, after 100 steps, what is the probability that I will be in state 1? So can you tell me that probability, or how would you calculate that probability? I can ask, what is the expected time of reaching state I if I start from state J? Okay, another fundamental question. What is the expected time of having visited every state given that you started in some initial state. And I can ask, a lot of questions like this that are really fundamental. So how can we try to tackle some of these questions?
You can do the first one by raising the transition matrix to the t power.
Yes, and I will discuss that right now. Okay, so let's look at the first question. Okay, so we want to understand how this system evolves and how can we have a handle on the probabilities as the system evolves. So let's do the following. So let's suppose that we start at state 1, okay, and we let the system evolve, and try to express the evolution mathematically. As we said, we have this transition matrix that's an equivalent representation. So since we're starting at state 1, I can represent that as a vector like this. Pi 0, as we said, is 1, 0, 0, 0. I'm in state 1 with probability 1. I'm in state 2 with probability 0. I'm in state 3 with probability 0. And I'm in state 4 with probability 0. That's the representation of my initial condition. And it turns out, as you suggested, if I take this vector and I multiply it with the transition matrix, here we go, I will get another vector. In this case, I will get the following vector, 0, half, 0, half. And if you look, this is going to be precisely, this is going to represent precisely the probabilities of being in a certain state after one time unit, after one step. So you can see if I start with state 1, then in the next step I will be in state 2 with probability half, and I will be in state n or state 4 with probability a half. So you see that's exactly what is written here. So this, so it's the same thing. So we can call this now pi 1. Pi 1 is basically the probability distribution of x1. Right? So this is the new now probabilistic state. After one time unit, these are the probabilities that I have. Now, what if I said, okay, after 2 steps, what are the probabilities? Well, you can guess what to do. You take pi 1, which is the probabilities after 1 step, and multiply by the transition matrix again, and you will get a new probabilistic state, pi 2. These are the probabilities after 2 steps. In general, if your initial, let's say, probabilistic state is represented by p1, p2, all the way up to pn, so let's call this pi 0. So the pi is the probability of being in state I, and these pi sum up to 1 because it's a probability distribution. After t steps, the probabilistic state is you take this initial probability distribution, you take your transition matrix, you raise it to the power t. Okay? And once you do that, we'll call this new vector, that vector you get is pi t sub t, distribution of xt, and pi sub t of I, the ith entry of pi t is the probability of being in state I after exactly t steps. And you don't have to think about this initial probabilistic state as an initial probabilistic state. You can say, if my current probabilistic state is p1 to pn, and I take t more steps, then this is the probability, the probabilistic state that I will end up in. Now, I did not prove this to you. I just stated it. It's not hard to prove. It's a good exercise. Okay, so in the homework, you will most likely prove this. Okay, and as I mean, it just follows from definition. There's nothing complicated. All right, So now I want to discuss like two very interesting properties of Markov chains. Very interesting and very important properties. The first one is related to the following question: what happens in the long run when I let the system evolve, when I let the drunk guy walk for like 1,000, 1,000,000 steps? Is there anything I can say about the probabilities of the states? Okay. And it turns out that you can say something very strong about the probability of the states. For this, we will need to make one small assumption. So we have to assume that our Markov chain is what's called aperiodic. For now, just ignore this condition. I will come back to it. I will and discuss it, but let's just ignore this condition for now. Then, as the system evolves, the probabilistic state, it turns out, converges to some limiting probabilistic state, some actual fixed limiting probabilistic state. In other words, what this means is that as t goes to infinity, okay, this is your initial state, doesn't matter what it is. As t goes to infinity, you take your vector, you multiply it by the transition matrix to the power t. This will converge to some fixed probability distribution, which we'll denote by pi. Okay? And this is going to be the same pi no matter what initial state you start with. And that's what's very interesting about it. Doesn't matter if you start in the first state or the 100th state or whatever state you want to start in. As t goes to infinity, the probability that you will end up in a certain state that converges to a certain fixed probability. And it's not surprising that, of course, if I now were to start with pi, let's say as my initial distribution, if I multiply it by the transition matrix, I'm going to get back pi. So if you know what an eigenvector and an eigenvalue is, you can say that pi is an eigenvector of the transition matrix, and the corresponding eigenvalue is 1. If you don't know what that means, it's okay. Just ignore what I said. But if you know, you might find it interesting. Now this pi is called the limiting distribution, but we also call it the stationary or invariant distribution. Right? It's stationary because when you apply the transition matrix to it, you don't change it. It's stationary. It's invariant. And this pi is unique. For example, let's look at this Markov chain that we looked at before. Sunny and rainy. I can calculate the stationary distribution, and I did it, and it is 5/6 and 1/6. How you should interpret this is as follows. You should think of it as, in the long run, it's going to be sunny 5/6 of the time, and it's going to be rainy 1/6 of the time. Okay? Now, what about this periodic business? So we assume that it was aperiodic. I'm not going to actually define to you formally what periodic means, but I will give you one example, and it should illustrate the point. So here is a periodic Markov chain. It's very simple, 2 states, 1 and 2. And there's one, so from 1, if you're in 1, there's 100% chance you're going to go to 2. And if you're in 2, there's 100% chance you're going to go back to 1. Now let's say pi 0, my initial distribution is 1, 0. So I start at state 1. What is going to be pi 1? 0, 1. What's going to be pi 2? 1, 0. What's going to be pi 3? 0, 1. 1, 0, and so on. So you see it's alternating between 0, 1, and 1, 0. Question?
Is the transition matrix PR Markov chain always a permutation matrix?
Is it always a permutation matrix?
Yeah.
Well,
Or they keep it when it's not?
what do you mean by permutation? I mean, you have probabilities.
The rows and columns switch back.
You mean a symmetric?
No, I mean an identity matrix where you switch the rows and columns.
Okay.
So, for instance, like this transition matrix should be 0, 1, 1, 0.
Right.
So, if every PR Markov chain of that sort, where you have only a single bond along each row and a single bond along each column?
No, of course not. I mean, entries are probabilities, right?
Yeah.
So you don't have to have any ones.
Oh, okay, I'll rephrase my question. Is every periodic Markov chain completely deterministic?
Is every?
Periodic Markov chain completely deterministic?
Oh, no, not necessarily. Yeah.
Are Turing machines technically Markov chains?
Not quite, because it evolves deterministically, right? So there is nothing random about a Turing machine. You can ask, what about a randomized Turing machine? And a randomized Turing machine, you can view it as a Markov chain if you want. If you look at the tree, the evolution tree, yeah, you can. Although it's not going to be a very interesting one. So it's not a useful point of view. Yeah.
Why can the limit not be some other eigenvector?
Say again?
Why can the limit not be some other eigenvector? Why is it always the same one?
Why is it always the same one?
Eigenvector.
Right. Why is it unique?
Yeah.
Right. Yeah. So it's a good question. Maybe it will show up in the homework. Yeah. All right. So coming back to this, the thing is though, okay, so this is periodic. So definitely it doesn't have a limiting distribution. It switches between 0, 1, and 1, 0. On the other hand, it does have a stage pi. If you look at this pi, which is half-half, it is a stationary invariant distribution. You multiply it with the transition matrix, you get back the original vector. So the intuition that, in the long run, it is going to be in state 1 half the time and state 2 half the time, it's actually correct. But on the other hand, there is no limiting distribution because it switches between these two distributions. And yeah, I mean, you can have much more complicated periodic Markov chains, but this is like the simplest one. Okay, so that's quite a remarkable property. That's a very interesting property of Markov chains. The second property that I want to discuss is the following. So let's look at this. Let's define this random variable, Tij. So what's Tij? It's the time it takes to reach state j, given that you started at state I. Okay. So in a lot of Markov chain analysis, this random variable comes up. It's an important random variable. What I want to say is actually about Tii. So the time it takes to return to I when you start from state I. And it turns out that the expected value of Tii is 1 over pi I, where pi is this limiting distribution. Okay? So think about that. So maybe in the limiting distribution, I have a state that has probability 1 over 100. So 1 over 100 of the time, I'm going to be in this state. Now, if I look at the following, if I start from that state and I ask, what is the expected time it takes to come back to that state? It's going to be 100. In 100 steps, I'm going to come back to it. Okay, so this is known as the mean recurrence theorem, by the way. That's the official name. It's quite useful. It's quite important. And again, if you want to, think about the intuition, so suppose we have some state whose limiting probability is 1 over 4. Well, then in the long run, you expect to be in that state n over 4 times, pi over pi I n times, right? So if it's like 1 over 4, then, it's like every n over 4 of the guys is going to be the red one, the I guy, the state I guy. And the average time, you can say, between successive visits to I, well, you could expect it. You would expect it to be like 4 if this was like 1 over 4 chance. Right, so that's some, somewhat vague intuition, but it's possible to turn this into an actual proof as well. Okay, so the summary so far is as follows. So what did we say? So the Markov chains can be characterized, completely characterized by the transition matrix. Let's call it K. So the entry Kij, the ijth entry in this matrix, is the probability that x1 is equal to j given x0 is equal to I. What is the probability of being in state I after exactly t steps? You can calculate this as follows. You take your initial distribution pi 0. You have your transition matrix K. You raise it to the power t. Right? So you multiply the initial distribution by k to the t, and that gives you some vector. That vector we denote by pi t, and you look at the ith entry of that vector, and that's the probability of being in state I after t steps. We've seen that there's a unique invariant distribution pi, where pi equals pi times k. If the Markov chain is aperiodic, we know that these pi sub t's, they converge to this pi. And also the last thing we said was, if you look at the expected number of steps you need to come back to state I, if you start from state I, that's going to be 1 over pi I.
Would we generally be given pi, or do we need to find it using like lineality?
Yeah, so no one's going to give you pi, but yeah, you can calculate it pretty easily. Yeah, that might be actually another homework question. Yeah. Yeah, I mean, this was on purpose that I didn't discuss how to compute pi, because yeah, it makes a good homework problem. But yeah, there are different ways you can do it. All right, so that's the basic mathematical representation and properties that we have time for. Of course, like, it's a huge field, and there's so many things you can discuss. You can easily have a course or two on it, but this is all for now. Let's look at some applications. Actually, I'm going to discuss two types of applications. The first one is going to be more like a theoretical application to theoretical computer science. And the second one, I'm going to discuss more practical applications. Let's start with the theoretical application. And this is going to be about the connectivity problem. Okay, so what's the connectivity problem? You're given some undirected graph. Okay, so this is an undirected graph, G, and two vertices, S and T. And your task is to figure out whether S and T are connected. Okay, if there's a path between S and T. So you output yes if that's the case, you output no if it's not the case. And this is a really fundamental problem in computer science. Like a lot of the problems you can encode it as a reachability problem in graphs. Now it's easy, so can we do this in polynomial time? Yes, so what can we do? Yes.
Search.
Search. What's your favorite search? AFS, BFS, CFS, DFS? Yeah, you can do like BFS or DFS. You pick your favorite search algorithm. That's going to run in polynomial time and do the job. So that's good. But our interest will be to do it efficiently with respect to the amount of memory or space you use. Okay, so in particular, this is the question that I want to ask. Can we do it using order log n space? BFS and DFS, all these search algorithms, they don't use order log n space. They use much more than that. Can we do it using order log n space? Now let's think about this. Order log n space. What can you do in order log n space? You have n vertices. Imagine you have thousands of vertices. In log n space, I can remember one vertex. The name of one vertex takes log n space to write down. So I can remember the name of one vertex. Since I have order log n space, that means I can remember like a constant number of vertices. That's fine. But really, that's pretty much all you can do. So if you imagine yourself like in this big maze, okay, this huge, gigantic maze, and you're like the Memento guy. Have you seen the movie? So you have very limited memory. You can sort of remember like locally where you are, maybe local information, but you can't really remember a lot about the general structure of the graph. So how do you get out of the maze if you have like so limited memory? You know, it doesn't seem possible, but maybe we can do it randomly, right? So what if I said, okay, let's try to come up with a randomized algorithm. Can we do it in log n space? So would randomness help? It's not clear whether it would help or not, but let's see if it would help. Now, if I asked you, okay, give me a randomized algorithm for this problem, what's like the most obvious algorithm that you think of?
Whenever you're at a given vertex, randomly pick one of its neighbors.
Okay, yeah. Randomly, do a random walk, basically, like the drunk guy. Just, simulate the walk of a drunk guy and hope that you will reach T after some reasonable amount of time. Okay, so here's that algorithm, a random walk algorithm. You start at the vertex S, so V is S, and you repeat for a certain number of times. Let's call it capital N for now. You pick a random neighbor of S. If it's T, you're done, you found T. If it's not T, you repeat this process. You pick a random neighbor of that vertex V and check if it's T or not. If it's not, pick a random vertex and so on. Okay, now what is the space, first of all, complexity of this? Well, it depends on what n is going to be. But if capital N is polynomial in n, then this counter I have for k is a variable. It's going from 1 to up to n. If capital N is polynomial in n, then I need only log n space, order log n space to represent that number. And other than k, the variable k, I have this variable v, which holds the name of a vertex, and that's also a log n space. So really, as long as n is polynomial in n, we're good. This is log space. But what about the success probability? I mean, the success probability has to be reasonably good so that we can say that we have a good randomized algorithm. So what is the success probability? Well, first of all, notice that if S and T are not connected, if they're disconnected, then our algorithm always gives the correct answer, no problem. So really, the interesting case is when S and T are connected, and we want to know now, when they are connected, what is the probability that my algorithm will say, yes, they are connected? What's the probability that my random walk that starts from S will actually reach T? Okay, so I want that probability to be non-negligible, some good probability. Okay, so let's analyze that. So that's what we're going to do. So random walk on undirected graph. So let's say we have some undirected graph with n nodes and m edges. And what we're going to do, as we said, we start at some vertex, and we're going to keep picking a random neighbor iteratively. Now let's say this is our undirected graph. This is, of course, this process is a Markov chain, right? And that shouldn't be surprising. I can give you the Markov chain. It's right there. So what I do is I change each edge, undirected edge, into two directed edges. Okay? And I write down the associated probabilities. Now, why does this edge have probability 1/3? Because there are 3 edges coming out of this state, this vertex. Okay? Here, there are 2 edges coming out of this, so they are both 1/2. Good. So that's how the directed Markov chain looks like. How does the transition matrix look like? First of all, here's the adjacency matrix of the graph. Right. So vertex 1 is connected to vertex 2, vertex 3, and vertex 4, and so on. Right. How would I obtain the transition matrix K from the adjacency matrix A? Mark.
You take the vector where the ith entry is 1/6 the degree of that vector.
Yeah, so we want to divide basically each row by the degree of that vertex. So we want to divide row 1 by the degree of vertex 1, row 2 by degree of vertex 2, row 3 by degree of vertex 3, and so on. And then what you will get is this matrix, and it's precisely going to be the transition matrix. Right? That makes sense?
How are you going to calculate that in log n space?
I'm not going to, because that's not what the algorithm does, right? Okay. Let's ask, how does the stationary distribution look like? We know there's going to be a stationary distribution. So let's consider this graph for a second. So in the long run, the stationary distribution is like a distribution in the long run with what probability you're going to be in a certain node vertex. So which vertex do you think has the highest probability? The middle one. Why? Why did you pick the middle one? Yes, another way to say that is it has the highest degree, right? So it would be great if, your intuition tells you that the stationary probability of a vertex should be somewhat proportional, in some sense, to its degree. And that turns out to be actually true. Okay, so Is pi proportional to degree I? Yes, it is. So you can show that actually the stationary distribution is going to be exactly the following. So the probability of vertex 1 is going to be degree 1 over 2m. The probability of vertex 2 is degree 2 over 2m, and so on. And why 2m at the denominator? Because that's the sum of the degrees. Okay, so 2m is the sum of the degrees. So if you add all of these up, it adds up to 1. It's a probability distribution. And since now we know what pi is, we can also determine what this expected value of tii is, the time it takes to come back to I when you start from vertex I. And that's the reciprocal of pi I, right? 2m over degree I. But what are we really interested in? When we come back to the algorithm, we start from vertex S, and we want to reach, assuming that S and T are connected, we want to see like how much time if my random walk will take to go from S to T. Right? That's really what I want to know. Not I to I, but S to T. So how about expected time for Tij, where I and j are different? And when I or j are connected. If they're not connected, if they're disconnected, well, then you'll never reach it anyway. So that's 0. So that's not interesting. But if they're connected, how much time does it take to go from I to j? And we can actually analyze this and get a bound on this. So to get a bound on this, let's pick a path from I to j. Fix some path from I to j. And let's call the vertices on this path I1, I2, I3, all the way up to IR, where I1 is the starting vertex I, and IR is the end vertex j. We know that R here, the number of vertices on this path, is at most n, the number of vertices in the graph. And now I'm interested in upper bounding expectation of Tij. So how can I upper bound Tij using this path? Mark.
Say like going from one to the next is like at worst 1 over n chances.
Okay.
So following each of those would be 1 over n to the n.
Right. So I mean, like forgetting the probabilities for now, I mean you have the right idea. So just look at the time. So the time it takes to go from I to j is definitely upper bounded by the time it takes to go from I1 to I2 first, and then the time it takes to go to I2 to I3, the time it takes to go I3 to I4, and so on. It's an upper bound because it doesn't have to take that route, the path that you're going from I to j. Right? It doesn't have to go through this, but if I force it to go through that, it's definitely an upper bound on the time. Okay? And once I have this upper bound, what am I going to do next? This should be automatic. What's that? So linearity of expectation. Okay? Expectation of sum of random variables, you immediately do linearity of expectation. So now I have this sum. So what can I do? So here's what's going to happen. So we will be able to show that each of these terms, Ti1, I2, or Ti2, I3, each of these expectations is actually at most 2m. Okay? So we're going to, in the next slide, that's exactly what I'm going to show. I'm going to show that these are at most 2m. But if it is at most 2m, then I know that there are n terms in this sum, so it's at most going to be 2mn. M is at most n choose 2, right? The number of edges is at most n choose 2. So this you can upper bound it by n cubed. Okay? So, and this works because of the following fact, that the expectation of TUV, where U and V, UV is an edge, is at most 2m. Okay, so given that, we have this. But, you know, if we accept this for now, then what we have shown is that the expectation of Tij is n cubed. In particular, I can think about going back to my algorithm again. I have S and T. The expected time it takes to go from S to T is n cubed, which is a good sign, right? I mean, if you think about it. But we'll come back to that. Let's first do this. Expectation of TUV is at most 2m when UV is an edge. Let's look at the neighbors of V. Okay, so we have U and V. That's the red edge that we are interested in. Now V has potentially other neighbors. Let's number them from U0 to UK. And U0 is going to be the U that we have initially. What we're going to do is actually, we're going to look at the expectation of TVV, the expected time it takes to come back to V when you start at vertex V. Now, why am I interested in that? And I know that that quantity is 2m over degree V, but why would that quantity be useful? How can I express that some way in terms of what I want, which is expectation of TUV? Well, you can think about the following. Well, when you start from V with 1 over k chance, with 1 over degree of V chance, I'm going to take the edge, the red edge, to U. Now, once I take that edge to U, to come back to V, what I have to do is go from U to V, the time it takes to go from U to V. So in some sense, you can say conditioned on the fact, on the event that in the first step, I take this edge V to U. The time that it takes to go from V to V, V to come back to V, will be 1, that edge, 1, plus the time it will take to go from U to V. Okay? Let me write it down. Okay? So this expectation of going from V to V is the following. By using the law of total expectation, which I think you did in recitation, you can write this expectation TVV as the expectation of TVV given that the first step is from V to UI times the probability that the first step is V to UI. Okay? So this is a very useful formula, by the way. So if you don't know it, this is very useful to write the expectation in this way. Now, what is the probability that the first step, V to UI, that's 1 over the degree of V. And if you tell me that the first step is V to UI, then the time it takes to go from V to V is going to be 1, the step that you took, V to UI, plus the time it will take you to then go from UI to V. Okay? So you can write this. And now I'm going to do something very trivial. I'm going to get rid of every term in the sum except for I equals 0. That's the only thing that's going to remain. So I take the I equals 0 term, so that's definitely going to be a lower bound. So that's going to be 1 over degree V times 1 plus expectation T U0 V. But U0 is U, of course. Now, why am I done? So I can definitely so now I have this inequality. So that upper bounds this. I can multiply both sides by degree of V, get rid of that. And then that's going to imply 2m is greater than 1 plus expectation of TUV. Okay, so actually we get to bound 2m minus 1, an upper bound of 2m minus 1 on expectation of TUV. But we can just forget about the 1 and say it's upper bounded by 2m. Okay, so it's an interesting proof. So please go over it again in your own time. But now we're in business. Okay, so we have proven that the expected time it takes to go from S to T is at most n cubed. And what I'm going to do now, I modify my, I specify in my algorithm what capital N is going to be. It's going to be 1,000 n cubed. Okay, I'm going to repeat for 1,000 n cubed steps the random walk. As we said, if S and T are disconnected, we give the correct answer. If S and T are connected, then what can we say? Well, we know expected time from S to T is n cubed. And this actually implies that the probability of error, the probability that I do an error is actually the probability that the time that it gets from S to T is more than 1,000 n cubed steps is upper bounded by 1 over 1,000. Why is this true? That follows from, again, by Markov, same Markov, Markov's inequality. So this is a very useful inequality in probability theory. It tells you that for any random variable x, the probability that x is more than some c times expected value of x is at most 1 over c. Okay, so you can take c to be a 1,000 here, up here, and you get the result from this inequality, Markov's inequality. Okay, so it is unlikely that the number of steps that is needed to go from S to T is going to exceed the expectation. Like it's going to be 1,000 times more than the expectation. It's not going to exceed the expectation. The probability of that happening is very low. Okay. So that's a way to do it in randomized logarithmic space. And this used to be for a long time a canonical example of a problem that we had a very nice space-efficient randomized algorithm, but we had no idea how to do it without using randomness in logarithmic space. So this remained open for a very long time. No one knew how to do it until this guy, Ömer Reingold, in 2004 showed that you can actually do this in deterministic logarithmic space. And it's one of the celebrated results in the area. It's pretty cool. It's very nice. All right, so that's a theoretical application. Let me now very quickly, in 5 minutes, go through some practical applications. I won't go into any details, but I want to just show you, give you some idea about how you can apply it in practice. So there are two common types of applications, I would say, of Markov chains. One is like you build a Markov chain as a statistical model of some real-world process. Okay, so your Markov chain is like a statistical model for a process that you observe in the world. And then you use your Markov chain to simulate for yourself that process. Like automatic text generation, automatic music composition, they fall into this category. Okay. And another way is to use Markov chains is like you use a measure associated with a certain Markov chain to approximate a quantity of interest to you. So for example, Google PageRank. Google PageRank is like a measure that is supposed to represent the reputation of a web page. And you approximate that quantity looking at a certain Markov chain and a measure associated with a certain Markov chain. Image segmentation also falls into this category. What I'm saying here on this slide is probably vague right now because you don't know exactly how these applications work. But now let me show you actually 3 of them very quickly. And then I'll show you this slide again and hopefully it will make actually more sense. So automatic text generation, how does that work? So this is like you want to generate superficially real-looking text given some sample document. Okay, so the idea is that you, from the sample document you have, so think of your sample document as, I don't know, the speeches of Obama. Okay, and you want to create new Obama speeches in some sense automatically. So you use a random walk. So you want to create this Markov chain that represents, that has the statistical information about Obama's speeches. And then once you have that, you can now generate new speeches using a random walk on that Markov chain. That's what I said. So how would you build the Markov chain? So for each document, for each word in the document, for each word you see, you create a node. Okay, a node for your Markov chain. And you're going to put an edge between two words, word 1 and word 2, if there is a sentence in the document in which word 2 comes after word 1. Okay, natural thing to do. And what are the probabilities going to be? The probabilities are going to reflect the frequency of those pair of words. So for example, let's say I have the word like in the document, and it is sometimes followed by the word a, it's sometimes followed by the word de, and sometimes followed by the word to. And I observe that like a appears 3 times, like de appears 4 times, like to appears 2 times. So the probabilities are going to be 3/9, 4/9, and 2/9. Okay? And then you can create, that's just your Markov chain, and I actually did implement this. I wrote the program, and I got a bunch of Obama speeches, and here's one thing that automatically came out. I mean, it doesn't make much sense, but it has humor value. But here's a way you can actually use it in a way that is, useful. You can say, okay, I'm going to build 2 Markov chains, one for Obama speeches, one for Bush speeches. Okay. Now I get a new quote from someone. I don't know if it came from Obama or if it came from Bush. Okay, what I can do is I can test it against my Markov models and see which of the models it fits better, the new quote. And I can predict with better than 50% chance, definitely, from which person the quote came from. And I did this as well, and it works pretty well. Image segmentation works like this. So given an image of an object, you want to know, let's say, very simplified version, which pixels correspond to, let's say, the background and which pixel corresponds to the object. So let's say you have some image that has one object and the rest is background. So you want to label each pixel object or background, and the user will, let's say, label some of the pixels for you. Okay. So what's the Markov model? So each pixel is going to be a state, a node, and there's going to be an edge between 2 pixels if they're adjacent to each other. And what is going to be the edge probabilities? Well, they're going to be based on how similar those pixels are with respect to their colors. If they're similar in color, they're going to have a high probability between them. Okay, and then what you do, so imagine it's going to be like a drunken walk. So imagine this is your picture. These red dots are the pixels. Okay, so the user gives you some labels. So this is, he says, this is background, this is object. And let's say you want to determine the label of this pixel right there. What you do is you start a random walk from this pixel, and you see which one is more likely. Is it more likely to reach the object pixel first or the background pixel first? Whichever is more likely, you pick that label for that pixel. I hope that makes sense. Again, let me spend 1 minute on PageRank as well. So how does the PageRank work? So you want to measure the reputation of a web page, and it's going to be measured by the number and reputation of links pointing to you. The way you do it is as follows. The Markov chain is basically going to be the web graph. So for each web page out there, you're going to have a node, a state in your Markov chain. What's going to be what are the edges in your Markov chain? So if there is a hyperlink from web page A to web page B, you put a link from A to B. Okay, so if CNN has a link to my web page, it doesn't, but if it did, there would be an edge from CNN to my web page. If A has M outgoing edges, each gets labeled 1 over M. So uniform distribution, basically. It could be the case that A has no outgoing edges, and you may get stuck in a web page. So to fix that, actually, what we do is we put an edge between such an A to actually all the web pages B and give it equal probability. So in a sense, when you hit A, when a random walker or a random surfer hits A, it will actually won't get stuck, but it will from there on jump to a random web page. Okay, so it might look something like this. You also have to do a little tweak. So you're trying to basically simulate how a random surfer would surf the web. So you start at some certain web page, you follow some links, and then you get bored. Maybe you go to some other random web page, right? So you do a little tweak. It's not too important. Just let's skip that. But basically, that's the Markov chain you build. And from that Markov chain, you can say, okay, what's the stationary distribution? So what's the probability of being in web page I in the long run? And that's exactly going to be the reputation of the web page. Okay? So the page rank, or the reputation of a web page, is, what is the probability that in the long run a random web surfer ends up in that web page. Okay, and as I said, Google says PageRank continues to be at the heart of the software, even though they use much more sophisticated tools right now. All right, so that's pretty much it. See you next week.